Today, I will take the chance to talk about my project, which is talking about production and characterization of lignin containing streams obtained with a lignocellulosic biorefinery framework under the supervision of Professor Andrea Qusay and from Hohenheim University and Dr. Irene Gebauer from Fraunhofer Center for Chemical Biotechnological Process, CPP. Fraunhofer is located in Saxony-Anhalt in a small town called Leuna, where I conduct my experiments. And Hohenheim, University of Hohenheim is located in Hohenheim in Stuttgart. In the next slides, I will explain the main objective of my work, which are first point, production and characterization of lignin and lignin-containing streams. The second objective is optimizing a two-stage process with mild conditions like low temperature and short time. The third point, or the third objective, is using the obtained fractions in different processes like fertilizer making process and hydrothermal processes. In order to achieve these goals, I have to select an efficient process and combine it with other processes. In this work, I selected the Organosolve as the main process to recover lignin from beechwood and combine this process with different processes like fungal pretreatment and pre-hydrolysis. At the beginning, I will talk about a general terms of Organosolve delignification process to who doesn't know about it. Organosolve is an environmentally friendly chemical process for the fractionation of lignocellulosic biomass, in which the delignification is achieved using organic solvents, in general ethanol, mixed with water. Many solvents were used in Organosolve process, but the most common is alcohols like ethanol, methanol, butanol, ethylene glycol, and glycerine. All these solvents are used for the delignification of lignocellulosic biomass. And for catalysts, mineral acids were used like hydrochloric acid, sulfuric acid, and phosphoric acid to stimulate the delignification process. And the Organosolve process operates at relatively high temperature range from 160 degrees to 200 degrees. At Fraunhofer CPP, as we see from this diagram, we have a large scale for Organosolve that operates at 170 degrees using H factor 1000 and 1% of sulfuric acid based on the dry mass of beechwood in 400 liters reactor, as we see in the diagram. We fractionate beechwood to get lignin, hemicellulose, and the pulp. Lignin are precipitated from the black liquor by adding water and then filtrate the obtained solution with filter press. Then the solid phase, which is lignin, is dried at 50 degrees under vacuum. Before drying, washed with water to remove residual sugars, ethanol, then dewatered and dried at 50 degrees under vacuum. For the hemicellulosic solution, we will get the xylose fraction after the recovery of ethanol, then evaporation of most of water. And the remaining pulp fibers will washed with plenty of water to remove the excess of ethanol, then dewatered and transferred to the next step, which is the enzymatic hydrolysis to produce a glucose solution. Organosolve process has many advantages, like the production of sulfur-free lignin, it can be run at a smaller scale compared with the craft process. The recovery of the used solvent is relatively easy, like ethanol. The recovery is quite easy. Less reagents are used during the process. On the other hand, there's many disadvantages for organosolve process, like using dilute and concentrated acids for a catalyst, relatively high operating temperatures, as I mentioned before, 160 to 200 degrees. It requires further purification and separation for lignin recovery. After finishing the pulping process, we will get black liquor, and we need further processes to precipitate lignin from this black liquor and then separate the xylose from the hemicellulosic solution. The concept of two-stage process is to recover the hemicellulose at the first stage, then recover the lignin in the second process, and lowering the amount of degradation compounds like furans, which act like enzyme and fermentation inhibitors. The question is why a combination between different processes are suggested? Why we suggest to make a combination between Organosolve and prehydrolysis, Organosolve and fungal pretreatment. From the literature, we found that the scientists suggest this combination to overcome the drawbacks of concentrated and dilute acids, to recover the cellulose in less recalcitrant form, and to aid the development of a process with lower energy costs. Now, I will move to more specific topic, which is talking about using fungal pretreatments with Organosolve process. I will talk about the effect of using the fungal pretreatment on the Organosolve delignification of beechwood and the characteristic of the recovered lignin. This was a joint work with the University of Santiago de Compostela in Spain in 2 G enzymes projects. In this work, we used a biological treatment, as I mentioned, fungal pretreatment using Ricci and Ibex fungi prior to the Organosolve. And we studied the effects of this process on the delignification of the beechwoods, the characteristic of the recovered lignin, as well as the enzymatic digestibility of the remaining residual solids, which is pulp. The concept of the fungal pretreatment is by attacking lignin and carbohydrates in lignocellulosic biomass in order to ensure lignin-free and cellulose-rich biomass for the next hydrolysis step and enhance the biomass digestibility. As the Organosolve, fungal pretreatment has advantages and disadvantages. And the advantages of fungal pretreatment are it's an environment-friendly process, enhances the enzymatic digestibility and low-cost process. On the other hand, the disadvantages are the process is take long time, needs large space, and require careful control of growth conditions. Now, let's describe the whole two-stage process of fungal pretreatment followed by the Organosolve delignification of beechwoods. This process was done on a small scale. First, we got the beechwood chips. Maybe we have 2 possibilities, maybe direct Organosolve in 1 liter per reactor at 155 degrees, or the second choice is to make the fungal pretreatment, which will start by taking about 100 grams of beechwood chips and 100 ml of tap water mixed in Finnerbach flasks and sterilized by autoclaving at 121 degrees for 35 minutes. After sterilization, we got sterilized wood chips. 24. Now we will go to the fungal treatment. About 24 plugs 4 by 4 millimeter fungal mycelium form fresh from fresh agar plates were added to each Fenerbahce flask and maintained in static culture in an oven at 30 degrees during 60 days. These are the Fenerbahce flask contain peach woods 0 day before the autoclave, and these the peach woods after 0 day after inculation, after we sterilized the peach wood and add the fungi. And these after 7 days of solid state fermentation process, and those are after 14 days, and finally after 60 days we got these. The two flasks are on the right are the control samples, which made without adding any fungi. In the middle is fungal pre-treated beechwood with Ibrahim type, and on the left is fungal pre-treated beechwood with Ibrahim. After that, we got fungal pre-treated beechwoods, but in the autoclave, as I mentioned, 1 liter per reactor at 155 degrees, milder conditions, 1% sulfuric acid for 160 minutes to get the black liquor after that, which contain lignin, hemicellulose, and degradation products. And we will get lignin by adding water to the black liquor. Lignin precipitates, then filtrates. We got lignin washed with water to remove the ethanol, residual sugars, and dried at 50 degrees under vacuum. And the liquid phase is, we evaporate ethanol from the liquid phase, or we recover ethanol from the liquid phase, so we can use it in another process. And we evaporate most of water to get the xylose and some degradation compounds. And the solid phase resulted after the Organosolve process is the fiber residues, cellulose fraction, washed with water, get rid of ethanol, sugars, and subjected to enzymatic hydrolysis using CTEC3 and HTEC3 at 50 degrees pH 5 for 24 hours to produce glucose and hydrolysis residues. Sorry. After finishing all the experiments, analysis of the collected samples is needed to know the yields of the recovered lignin and pulp, the chemical composition of the recovered lignin and pulp, the characteristic of the recovered lignin like elemental analysis, carboxyl and phenolic hydroxyl groups content, molecular weights and dispersity, and the thermal properties of the recovered lignin. In the next slides, I will talk about the yields and chemical composition of pulp. In this slides, we will see we have to know the chemical composition of the autoclaved beechwood, the control sample, and the fungal pre-treated beechwood is necessary to know the composition for other calculation like yield and composition. As we see, the main component of this wood is glucan, xylan, lignin, and acetic acid. And we see that the composition is slightly affected by the autoclave, where the amount of glucan compared to the autoclave, compared to the original beechwood without any autoclave, is decreased. Also, the amount of xylan decreased, and as well as the amounts of lignin also decreased. And this is due to the high cellulitic and hemicellulitic activity of the used fungus. In this slide, we see the pulp and lignin yields after a complete process of fungal pre-treatment and Organosolve. We see that compared to the control sample, the pulp yield slightly decreased, and the lignin yields decreased in case of using aerobics for fungal pretreatment, but in case of using Ritchie is slightly improved, not too much. And this is how we can measure the efficiency of the process from the lignin yields and from the lignin from the pulp yields. The only explanation for these results that the fungal pretreatment affects the polysaccharides removal in Organosolve pulping, so the pulp decreased. In the next slides, we will show the composition of the obtained pulp samples. As we see that the pulp composed mainly from glucan, xylan, residual lignin, and acetic acid. We see that the fungal pretreatment succeed in recovering more glucan, and the xylan is compared to the control sample almost the same, not changed, and the residual lignin that stayed or stuck in the pulp after the Organosolve delignification decreased after using fungal pretreatments. And this is significant in after using aerobics. And the acetic acid amounts in the pulp almost the same compared to the control sample. So the lowest residual lignin was in case of using aerobics. In the next slides, I will explain the characteristic of the extracted lignin, like the chemical composition, elemental analysis, carboxyl and phenolic hydroxyl groups, content, molecular weight, and polydispersity, and the thermogravimetric analysis or thermal probabilities of lignin. In this slide, I expressed the chemical composition of the recovered lignin, which means that lignin is composed from Clason lignin and acid-soluble lignin. Clason lignin is the same of acid-insoluble lignin. As we see from the results that the acid-insoluble lignin amounts or Clason lignin decreased after the fungal pretreatment, and the acid-soluble lignin amounts increased, where the xylan amount is the same in all samples. In this slides, we did the elemental analysis for the recovered lignin to know the ratio of hydrogen to carbon ratios and oxygen to carbon ratios. And we see that we got lower ratios. And this is due to maybe lignin is probably oxidized by the fungi. And in these slides, we express the amounts of carboxyl and phenolic hydroxyl group content in the recovered lignin, as we see compared to the control sample. Treatment with Ritchie fungi reduced the amount of phenolic hydroxyl group contents due to also the oxidation. In the next slides, the most important effect was on the characteristic of lignin was the molecular weight. We see that molecular weight increased compared to the control sample, and the highest molecular weight obtained after using aerobics. And also the dispersity of the lignin was high compared to the control sample, but when we want to compare to like a normal Organosolve process, the combination between fungal pretreatment and Organosolve obtained lignin with much higher molecular weight and dispersity. And now let's move to the thermal properties of lignin. We did the TGA for the lignin. At the beginning, I have to explain some definitions for the TGA. TG is the weight loss of compounds in relation to the temperature of the thermal degradation, and DTG is the rate of weight loss. In each curve, we have 3 zones. The first zone is the initial weight loss due to the water evaporation. It ranges from 0 to about 150 degrees, as well as the gaseous emission of carbon monoxide, carbon dioxide, and other pyrolysis products. The second zone, which ranges from more than 150 degrees until 500 degrees, is due to the weight loss phase related to lignin. The extended range is due to the complex structure of lignin, fragmentation of inter-unit linkage between phenolic hydroxyl carbonyl and benzylic hydroxyl groups, releasing monomeric phenols. This is why we got a wide range from about 180 until 50 degrees. And the third zone was after 500 degrees is related to the condensation and or decomposition reactions of the aromatic ring. The small peak in the second zone is related to the degradation of hemicellulose, which is confirmed the result that obtained from the chemical composition of lignin. As I mentioned in the previous slides, that lignin contain small amounts of xylose, and the thermal, the TGA results confirmed this result. And we have to conclude that the fungal pretreatment has no effect on the decomposition of lignin. After that, the third fraction from the process is the residual fibers. We have to subject these fibers to enzymatic hydrolysis process to produce or enhance the production of glucose, where this process is done using CTK3 and HTK3, as I mentioned, novo enzymes at pH 5 at 50 degrees for 24 hours. On the left curve, this is the analysis of the hydrolysis lignin, is the solid phase obtained after the enzymatic hydrolysis. On the right side is the liquid phase obtained after the enzymatic hydrolysis. We are interested in the liquid phase. As we see, we got the highest glucan in case of using Ritchie, and the lowest was in case of using Ibex. It seems that the fungal pretreatment slightly improved the enzymatic digestibility. Last but not least, we conclude with the following findings. The fungal pretreatment has no effect on the yield of lignin, but it affected its the characteristic of lignin. Also, autoclave has a significant effect on the composition of beechwood. Ibex fungi reduced the yield of lignin, while the Ritchie fungi has no effect on the yield. Pretreatment with fungi decreased the acid insoluble lignin, which is Clayson lignin, and increased the acid soluble lignin. Pretreatment with Ritchie fungi improved the production of glucose after the enzymatic hydrolysis of residual pulp. Treatment with fungus affected the characteristic of the recovered lignin by increasing the molecular weight and polydispersity. And thanks for the European Union Horizon 2020 Research and Innovation Program under Marie Curie Grant Agreement number 721991. And thanks for your attention. That's all.